In this lecture, we will be doing an example of polar graphing, and this will be an example that has a graph that looks like a flower. So recall our strategy. Our first step is to try and detect symmetries. And so we use these different points to try and detect symmetries in the polar equation, which translates into symmetries in the graphs. So for example, if we have the point in the xy plane with polar coordinates r theta, and we were trying to detect, say, symmetry about the y-axis, well, we could think how these polar coordinates relate, and we have r and theta for our original polar coordinates, and we note that for our point that's reflected about the y-axis, we can have the same r, the same distance from the origin, and we take that theta, which also is over here, thus the overall angle is pi minus theta, and we have this point here represented by r, pi minus theta. So we can check for symmetries using these points. So the example we will be working with in this lecture is r equals 2 times cosine of 2 theta. So first, let's try and detect x-axis symmetry. And so can we replace r and theta with these counterparts, r and minus theta, and recover the original equation? And we see, if we replace r on the left, and this theta here by minus theta, we actually do recover things because the evenness of cosine allow us to replace cosine of minus 2 theta with cosine of 2 theta. And again, that's because cosine is an even function. So we do have x-axis symmetry. What about y-axis symmetry? Well, let's check replacing r and theta with r and pi minus theta. If we do that, on the right we have 2 cosine of 2 times the quantity pi minus theta, or 2 cosine of 2 pi minus 2 theta. And we can use our trig identity that cosine of a minus b is cosine of a times cosine of b plus sine of a times sine of b, where a and b are played by 2 pi and 2 theta. So this becomes 2 times the quantity cosine of 2 pi times cosine of 2 theta plus sine of 2 pi times sine of 2 theta. Sine of 2 pi we know is 0. Cosine of 2 pi is 1. And so this will be 2 times cosine 2 theta. And that, with r, playing the role of r, they are equal. And so we do also get y-axis symmetry. So we've detected 2 symmetries, which is quite helpful. If we tried to detect symmetry about the origin, we're checking minus r and replacing theta with theta. In that case, we cannot conclude origin symmetry because we would need to have r and 2 cosine 2 theta. We would need to recover the original equation, so we cannot conclude. And again, this doesn't mean it's not there. There are infinitely many ways to characterize the point r theta reflected through the origin. This is just one of them. So this doesn't mean that the origin symmetry is not there. It just means we could not detect it. And let's revisit our graphing technique. The idea is we work in two spaces. We work in r theta space, where we think about the polar equation being graphed with r and theta as Cartesian coordinates. And then we use the information in that graph to draw the graph in the xy plane when we interpret r and theta as polar coordinates. So let's work on our graph r equals 2 times cosine of 2 theta. So first of all, let's think about the graph of r equals cosine of theta. And let's work on the interval 0 to 2 pi. So we know our graph of cosine theta looks like this. It has roots at pi over 2 and 3 pi over 2. It hits 1 at theta is 0. It hits minus 1 at theta is pi. And it hits 1 at theta is 2 pi. Now if we change from cosine of theta to cosine of 2 theta, that effectively speeds up this wave. So if we look at this now, this root will happen at pi over 4. And this minus 1 at pi over 2. And so we can see how this is really a speeding up of things. We have a root at 5 pi over 4, and then at 3 pi over 2, we have it being minus 1. At 7 pi over 4, we have a root, and at 2 pi, we have it being equal to 1. So this is what again, we're working in r theta space. This is the graph of r equals cosine of 2 theta. And then to modify this to be 2 times cosine of 2 theta, we need only increase the amplitude. Instead of going from minus 1 to 1, it will go from minus 2 to 2. So if this is 2 and this is minus 2, we have a root here at, say we have this as pi over 4. Here at pi over 2. So we look something like this. So now that we have this sketch, let's move forward with using it to understand what this graph says when interpreted as polar coordinates in the xy plane. So here we have the same graph that we just worked out. And let's think about what it means. And so let's break it into pieces. So we have a good natural first piece to use is this stretch here where theta ranges between 0 and pi over 4. 0 to pi over 4 as a range for theta is 0 to the line y equals x. So we can draw the line theta equals pi over 4, and we know theta ranging over the interval 0 to pi over 4 is this angular region here, this bottom part of the first quadrant. And the story that this tells us is that as theta, starting from 0, increases to pi over 4, the distance from the origin, r, begins at 2, and as we increase theta, as we sweep out in this counterclockwise direction, that distance from the origin falls from 2 all the way down to 0. So we get something that looks like this. So as we increase that theta, we're falling to the origin, hitting the origin actually at r equals 0. So we're doing something like this. If we look at the next range, theta going from pi over 4 to pi over 2, so we'll highlight that in blue. The story we have there is, so we're sweeping out this region here as theta, so we can write this out, increases from pi over 4 to pi over 2, r decreases from 0 to minus 2. And so we have to think a little bit differently because we're dealing with a negative range for r. But as we sweep this out, let's think about if it was positive. Suppose instead of decreasing from 0 to negative 2, r was increasing from 0 to minus 2. So as we sweep this out, r would increase from 0 up to 2. But because r is negative, we have to reflect that through the origin. And reflecting this piece through the origin will give us a piece down here that looks like this. And we can continue. But we also can realize a couple things here. Recall our symmetries. Recall that we had determined that we had both x-axis and y-axis symmetry. And that can save us a lot of work. X-axis symmetry means we can take this piece here and reflect about the x-axis. We can also reflect this piece down here in the third quadrant about the x-axis. And so that lavender color, again, is coming from x-axis symmetry. But again, we also have y-axis symmetry. So for y-axis symmetry, in orange, we can reflect this blue piece in the third quadrant we can also reflect this lavender piece that's in the second quadrant over to the first quadrant. And this entire petal in the first and fourth quadrants can also be reflected over. And we get a ton of the graph by exploiting these symmetries. Now, it's also true that we could have just continued through this process here. And we would have continued, we started here, and we would have continued to trace out this flower, this four-leafed flower. But you can save yourself a lot of work by exploiting these kinds of symmetries. But the idea really is to combine the two. Symmetries are not enough to graph it. You're going to have to do some graphing. But this approach of using this Cartesian interpretation of the r-theta relationship to then tell a story about what's happening when you now think about that r-theta relationship as a polar relationship in the xy plane is quite a powerful graphing technique. And a better drawn picture is given here, where you see the actual four-leaf flower. That is r equals 2 cosine 2 theta in polar.